Note at conditions of maximum power, the Thevenin's equivalent voltage source is supplying 17 watts of real power to the whole circuit, yet only 8.5 watts is getting to our load. This is to suggest that maximum power conditions, although representing conditions of peak real power delivery, aren't exactly the most efficient power delivery conditions. At conditions of maximum power, this represents an efficiency of only 50%. It needn't be surprising that maximum power conditions are not efficient conditions. Maximum power conditions are as inefficient as efficient conditions are less than powerful. Speaking of conditions at other than maximum power conditions, consider the following scenarios. As an exercise to the viewer, I invite you to calculate the apparent, real, and reactive power delivered to the load, as well as the efficiency of real power delivery for the following load conditions. 200 ohms at an angle of positive 20 degrees, 200 ohms at an angle of 0 degrees, 84.7 ohms at an angle of negative 53.8 degrees, and finally 504.7 ohms at an angle of negative 7.8 degrees. By all means, pause the lecture and try this on your own. You note it may be helpful to resolve the impedance values into the rectangular equivalents before resorting to extensive calculations. You should notice something very interesting for the last two scenarios. If you're tracking, you should have obtained the following results. In the occasion when the variable load impedance is 200 ohms at an angle of positive 20 degrees, we might anticipate not equal and opposite amounts of reactive power canceling each other out as in the maximum power condition, but rather consumption of twice the amount of reactive power. As a result, real power delivered to the load might be less. Let's see if this is the case. An application of the voltage divider rule suggests voltage across the load is 40 volts at an angle of 0 degrees. A subsequent application of Ohm's law suggests that current through the load will be 200 milliamperes at an angle of negative 20 degrees. The AC power formula suggests the load experiences 8 volt amperes of apparent power, 7.5 watts of which is directed towards real power, and positive 2.7 bars is directed towards a reactive interchange. As one might expect, real power delivered to the load isn't as large as maximum power conditions. In this scenario, efficiency is 50%. In the occasion when the variable load impedance is 200 ohms at an angle of 0, we again might anticipate not equal and opposite amounts of reactive power canceling each other out as in the maximum power condition. As a result, real power delivered to the load might be less. Let's see if this is the case. An application of the voltage divider rule suggests voltage across the load will be 40.6 volts at an angle of negative 10 degrees. A subsequent application of AC Ohm's law suggests current through the load will be 203.1 milliamperes at an angle of negative 10 degrees. Note, given the load is purely resistive in nature, voltage and current appear to be in phase with each other. The AC power formula suggests the load experiences 8.2 volt amperes of apparent power, 8.2 watts of which is directed towards real power, and 0 vars is directed towards a reactive interchange. As one might expect, real power delivered to the load isn't as large as maximum power conditions. Efficiency in this scenario is roughly 51.5%. The remaining two scenarios illustrate something interesting. In the occasion, the variable load impedance is 84.7 ohms at an angle of negative 53.8 degrees. This presents an impedance of 50 minus J68.4 when expressed using rectangular format. Note the imaginary reactive portion is in fact equal and opposite to the imaginary reactive portion of the Thevenin's equivalent impedance, although the real resistive portion is substantially smaller. As such, we might anticipate equal and opposite amounts of reactive power to cancel each other out, as in the maximum power condition. However, given a smaller resistive portion, we might expect it to draw more current, however experience a smaller voltage drop. As a result, our load will dissipate less real power. Let's see if this is the case. An application of the voltage divider rule suggests voltage across the load will be 28.5 volts at an angle of negative 53.8 degrees. An application of Ohm's law suggests current through the load will be 336.2 milliamperes at an angle of 0 degrees. Note source current appears to be in phase with the supply voltage, a clear indicator that equal and opposite amounts of reactive power are canceling each other out. As we anticipated, the smaller load draws more current, but experiences less of a voltage drop. The AC power formula suggests the load experiences 9.6 volt amperes of apparent power, 5.7 watts of which is directed towards real power, and negative 7.7 bars is directed towards a reactive interchange. As one might expect, real power delivered to the load isn't as large as maximum power conditions. Efficiency in this scenario is only 21%. Finally, in the occasion when the variable load impedance is set to 504.7 ohms at an angle of negative 7.8 degrees, this presents an impedance of roughly 500 minus J68.4 when expressed using rectangular format. Note the imaginary reactive portion is in fact equal and opposite to the imaginary reactive portion of the Thevenin's equivalent impedance, although the real resistive portion is substantially larger. As such, we might anticipate equal and opposite amounts of reactive power to cancel each other out, as in the maximum power condition. However, given a larger resistive portion of the load, we might experience a larger voltage drop, however, draw less current. As a result, our load might dissipate less real power. Let's see if this is the case. An application of the AC voltage divider rule suggests voltage across the load will be 58.7 volts at an angle of negative 7.8 degrees. A subsequent application of AC Ohm's law suggests current through the load will be 116.3 milliamperes at an angle of 0 degrees. Note source current appears to be in phase with the supply voltage, a clear indicator that equal and opposite amounts of reactive power are canceling each other out. As we anticipated, the larger load experiences more of a voltage drop, but draws less current. The AC power formula suggests the load experiences 6.8 volt amperes of apparent power, approximately 6.8 watts of which is directed towards real power, and negative 925 millivars is directed towards the reactive interchange. As one might expect, real power delivered to the load is not as large as maximum power conditions. Efficiency in this scenario is 72.3%. Power is not nearly as high as maximum power conditions, although this scenario represents a far more efficient means of delivery. You note with both magnitude and angle being variable quantities for our load impedance and AC power having both real and reactive dimensions, the maximum power transfer theorem as applied to AC circuits does not readily lend itself to easily discernible graphs, as did the DC maximum power transfer theorem. This being said, I hope the last series of illustrated examples demonstrated an important point. It should be obvious that maximum power conditions are occasions in which equal and opposite amounts of reactive power cancel each other out. If the load has too much or too little of a certain type of reactive impedance, this balance is upset. As a result, real power delivered to the load would decrease. Even in scenarios with equal and opposite amounts of reactive power, real power delivery only peaks when the real resistive portion of the load equals that of the real resistive portion of the Thevenin's equivalent impedance. A smaller resistive portion of the load would experience more current but less voltage. Similarly, a larger real resistive portion of the load would experience more voltage but less current. The maximum power condition represents a compromise condition in which not one, not two, but rather three interrelated quantities, voltage and current and power factor, a mathematical byproduct of relative phase shift, form a maximum product. In summary, a load impedance experiences maximum power conditions if and only if it is the complex conjugate of the Thevenin's equivalent impedance. Alright, that's about it for now. We'll examine illustrated examples of Thevenin's theorem and the maximum power transfer theorem in later lectures. In conclusion, we learned a variable load impedance will receive maximum real power from a circuit when its impedance is the complex conjugate of the Thevenin's equivalent impedance for that circuit. Additionally, we discussed electrical properties like voltage, current, apparent, real, and reactive power and efficiency for various load conditions. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.